The next session will be moderated by, will be chaired by Alessia Platania, who is an associate professor at Niels Bohr Institute in Copenhagen.
I already have the microphone, so this one is for the audience, I guess. Oh, okay, that's good. All right. Great. All right, so sorry, thanks for the patience and sorry for the slight delay. So we are going to have now a session on the theoretical frameworks and the guiding principles for fundamental physics. And according to the instructions that I received from Luca, there will be a first part on that is a Q&A related, maybe the volume is quite okay, that's no, it's fine. Okay, the first part will be a Q&A related to the talks of today, and the second part will be an open discussion on the broad topic of theoretical frameworks and the guiding principles for fundamental physics. That is today's topic. That's my list that should not go during the discussion. Yes, but in particular, we are going to discussing during the discussions on quantum gravity. Since here we have 5 experts on the topic of quantum gravity, and this is indeed what we got an overview of in the talks from today, quantum gravity and effective field theory. But let's start the session with a Q&A on today's talk. So if you have additional questions related to the talks from today, you can ask to any of the speakers. Now, Javan.
I have 2 questions to 2 speakers. So, okay, let me ask first question to Benjamin. I was confused about when you mentioned swampland in the asymptotic safety program. So, as far as I understand, asymptotic safety approach to quantum gravity is 4 dimensions and based on the principle of reaching asymptotic safety towards the UV scales. But swampland in string theory is issue related to compactification and getting a potential related that supports the physical phase. What are you speaking about? Totally different swampland and no relation to string theory. But then at the end of the day, at the end of the slides, you kind of mentioned string theory. I'm lost.
Okay, maybe let me clarify what I mean by swampland or landscape. So I would describe it like that. You have the space of all effective field theories without gravity, and you ask the question, can I find any quantum gravity theory that UV completes this EFT? And the set of EFTs that can be completed by really any, doesn't matter whether it's string theory, whatever, that's in the landscape. And whichever not, I would call it swampland. It's not really related to compactification or anything.
So there's no common link to string theory.
Well, then now you can ask additional questions, right? So you can compute the landscape in string theory, you can compute the landscape in asymptotic safety or your favorite theory, and you can ask, do landscapes intersect? Are they the same? Is there any part of the EFT landscape that is in the swampland for any kind of theory? So these kind of questions, right? You can ask.
So I'll switch to my second question to John. I was very interested in the remark you made about when we have a renormalizable theory like quadratic gravity and the Stravinsky inflation, we have inflationary scale, so we kind of avoid reaching Planck scales. That is very interesting. So can you elaborate on that, what you exactly mean? So that means we don't have to worry about Planck scale issues at all. We don't reach fields.
So the interesting feature is that the theory changes not at the Planck scale, but at the Meter scale, if the couplings are weak or small. And that that seems to say that the theory changes character at that scale and is different beyond that, in a way that such that the Planck scale isn't the real issue anymore, was already changed. The issue of whether it becomes weak coupled at that scale, I'd say, is the weakest part of the argument that it presented. We don't understand that well. But it would be quite lovely if it did stay in a weak couple of machine plastic plastics. That's a hope of the couple.
Are there other questions? I see George, what's up?
Hi, I have a question for Professors Anselmi and Sagnotti, and of course also other speakers are welcome to answer. So my question is very general, and it's about predictions from string theory. Since you seem to express very different viewpoints on it, I would like both of you to elaborate more on this.
Yeah, for me the point is the one that I said that in the talk. Maybe I can summarize it in the following way. We cannot make experiments in quantum gravity in laboratories. So there is only one experiment in quantum gravity that is going on, which is the universe. We cannot have much data. And most of scientific discoveries proceed which way? By means of genius intuition? I don't believe so. It's like guessing the image in a puzzle where you collect the pieces of the puzzle. Think of Maxwell equations. Maxwell added one term to close the whole equations because he knew the others. Think of the discovery of the omega minus in the decuplet. 9 ingredients were known and the 10th was easy to guess. Think of the Standard Model. A lot of data was available and the symmetry breaking mechanism was guessed to complete it. But in quantum gravity, we have nothing. Unless gravity is not as special as people think. And so if you put it in a different perspective and you think that there is a bigger puzzle, which is 4 interactions of nature, we know how to quantize 3 out of 4. Well, 1/4 is a big gap. But I take the most conservative attitude, which is I check what worked in the other 3, and I relax the minimum assumptions. I do not want to relax unitarity, that is my bias. There are people who want to relax that. I don't think it is reasonable, but you have to make a bet, of course. And causality is a very, very weak principle. I think you can renounce it. So every other approach for me is gratuitous, because if you start saying that gravity is special with no data, yeah, you can introduce holograms, loops, strings, but I don't see how many hopes you can have to guess it right.
But this doesn't mean that string theory cannot or does not make any predictions.
Well, tell me the predictions if you think
My point is that we tend to forget that the so-called problem of string theory with making definite predictions is a problem of gravity. You will all grant me that gravity doesn't have a global minimum principle for energy, because energy is an exact story, and that fact reverberates in the inability of making any statements beyond local perturbations or stability, for instance, for the size of the extra dimensions. So what can you do? What I'm trying to show you is perhaps a humble way of approaching one corner of the story. And the corner of the story has to do with supersymmetry, because most of what has been studied in string theory is in the supersymmetric framework. Supersymmetry is a very beautiful symmetry, but it's a little bit like confining analysis to analytic functions. It's beautiful. You can do integrals much more easily than with arbitrary functions, but it's not general. And so what happens if you break supersymmetry? To some extent, the whole building falls apart, as I'm trying to show you. But it doesn't fall apart as badly as you would imagine. And it even has some predictions, if you want, because there are some parameters that the theory fixes. For instance, this exponent that the theory fixes is one prediction. And it has some consequences on this inflationary dynamics, if you believe it. Now, whether this consequence is correct or not, we have to see. What we know now is essentially a postdiction. The CFD spectrum has some lack of power on the first multiples, if you believe it, because there is also the very subtle issue of cosmic variance. You have few images of the sky there, so the fluctuations depend on how much you believe it. We have to see what Slava believes, because he knows more than all of us about this story. I have the feeling that there is some indication there, and that's why I tend to pursue it. Now, on the grand scheme, I repeat that the key problem is gravity, which doesn't have a global minimum principle. You can say, then a theory which has more than 4 dimensions is doomed not to be predicted. That's fine. We can take that. Or perhaps we could say something that my colleagues never state, but it's true. We don't even know how to write the full equations of string theory, let alone quantize the full equations. We write down the low-energy effective field theory, we write down scattering amplitudes, and there is a definite prediction there, which killed string theory in the 70s, the fact that the amplitudes decay exponentially with energy, which contradicted the deep inelastic scattering experiments and got the theory pushed aside by QCD at the right time. If that scale is changed, the phenomenon of damping in energy is still present and is at the root of the ultraviolet finiteness. That's a fact. Stop here for now.
Are there other questions related to today's talk?
Hi, thanks for your talks today. So, more than one time today, he came up that the causal structure at the fundamental level has no, like, physical, it's not that it doesn't have physical meaning, but it doesn't make sense at some point. So my question is, if you don't have causality at the fundamental level, what's behind it? What do we have at the fundamental level? If causality is something that emerges later.
To me?
To everyone. Everyone who wants to.
Can I interject? It's good to distinguish between structure. It's good to distinguish between causal structure, right, which is a property of even an empty space-time, and then causal behavior of some matter fields or other stuff that are, that are put in this space-time. The first is, of course, if you do non-perturbative convergence of the type I'm doing, you are in the first place concerned with is the causal structure of that space, like something that emerges, or do I have to put it in some way, right? So people always fall in love with the idea that everything should emerge, right? But of course, then you have to change the mechanism, and no one has been able to do that. So one has to face actually the reality. So probably having to put it in, and what kind of the lattice approaches have shown is, all models one has studied that were purely Euclidean do not show any emergence of, the notion of time or the causal structure.
Yeah, exactly. Also, another question that I have in mind, like, is it the same thing to talk about time and causal structure? Like, can you have like causal structure without a concept of time, and vice versa? Can you have like
No, that's
time?
difficult. No, that's difficult. I mean, causal structure, of course, means cause and effect, right? There are causal relations between things, or things are not causally related. That requires some kind of magical properties, including time, the notion of time. So when you think about a merger, of course, you have nothing of the sort. It's just wiped out, and you have then to explain how it comes back, which is not such an issue when you're just working with flat space-time, because then you have all standard repercussions. But I think probably what Damian was referring more to causal behavior of matter, or what did you mean? That has as a prerequisite already that there is some causal structure with respect to which I can make such statements.
Well, to answer your question, you are asking if you give up causality, what is in its place?
Yeah, I mean, I was trying to imagine like if we were able to like take a look at the, I don't know, the quantum level without disturbing it too much, like if there is no causal structure at the fundamental level, how does it, like, there are correlations between the different systems, how like they interact, like when they interact?
Yes, so I think the price to pay is very little, because actually in quantum field theory we don't really talk about causality. In textbooks you have causality studied at the level of the propagator. If you want, there is Bogoliubov causality, which is an identity for the S matrix. Actually, it's an identity for correlation functions. It's not an identity for amplitudes. And then you have the statement about commutators of operators, which should be zero at space-like separated points. But the point about these definitions is that they involve operators or correlation functions, which may be off-shell and page dependent. So you can do quantum field theory without causality. That's what we have been doing for decades. And there is nothing that you need in its place. So if then you have a theory that really tells you that there is not even a hope to order events chronologically below a certain amount of time, you are not giving up that much. So I view things in the following way as sort of duality. You use coordinates and time, space-time, if you want to describe the macroscopic world. Black holes, you would never use momentum space to describe black holes. That's suicidal. On the other hand, if you want to go to very short distances, you use energy momentum. And with those, you can go up to arbitrarily high energies. You don't need space and time, actually. That's not what you do. That's why I do not think that quantum gravity is that different from the other interactions of nature, because space-time concerns the macroscopic world. So.
There was another question next.
Yeah, thanks. Perhaps related to this question, and perhaps more focused on John and Damiano. When we talk about this causality break at a certain level, and then it returning at some point, and then from this point on, then we have the normal structure of time. I'm very confused about how this is defined, right? If there's no time ordering at a point, and at some point there is, the whole definition of point, is it not related to time itself? I feel very confused about this. Like, is it certain?
Okay, so I can probably discuss this starting from an idea of Dirac that you can find in Jackson's book Classical Electrodynamics. You may remember that you know that a radiating charged particle that is accelerated radiates. And you can write down an effective high derivative equation, which involves a correction which is called Abraham-Lorentz force, which has runaway solutions. Okay? And write down this. Very simple. Instead of having F equal
There is a
N.
whiteboard.
Oh, there is? No.
Yes.
Just be careful, it's not quite
It's not stable.
So instead of having F equal MA, you have F equal MA plus, let me say, some constant which is proportional to the square of the electric charge. And this is an effective equation, but it's higher derivative, so it has runaway solutions. It's not a nice Cauchy problem behind this equation. Dirac has this idea. Because when I used to teach this in the university, my guess was if I can do this in gravity, then I do gravity. So you write it this way. And then you invert this operator. Okay. Of course, now you have no higher derivatives, but you have an ambiguity in defining this operator. And Dirac says, since tau is a constant, the radiating power that is proportional to the electric charge, I want to make the limit E equals 0 meaningful, then there is only one kernel, and that is like this. Which means that you have an equation MA equal F, but actually F is not F, it's a sum from T to infinity. You need to know the force, the external force in the future to predict the future. Okay? But you have a damping factor here. So you just need a little bit of future to predict the future. Which means that you need to, this is 10 to the minus 13 seconds. And so you need to bet that nothing really important happens in 10 to the minus 13 seconds to predict what happens in 1 second. Okay? Now, this is the meaning of this. And if you might not know, this is what we always do. Always do. Because that's why the price is so little to pay. In special relativity, we are here. What we know is just our past likelihood. But at some point in the future, we will be here. How can you predict what happens there? Something can sneak in. So you cannot predict anything in special relativity, unless you know something, the initial conditions at minus infinity. So that's why I advise people to be careful about raising fundamental principles to something that is too much with respect to what we do every day, basically. You always make a bet. In this case, you see it, and in the other case, you see it. I don't know if I...
Yeah, that really answers. I just find it funny that we just have this for time and not necessarily for space. I mean, okay, then you just give an example for special relativity where I guess they're the same structure, but I mean, where I was going with this is like, there's not a suggestion that time itself is a verdient property. Like, not from your perspective, I guess, no, but...
The time is an emergent property, yes.
But perhaps that is maybe one discussion that
I have a T that's a coordinate, but if you want to interpret it as we normally interpret it, yes, you can use it only for intervals of time that are larger than a certain amount, minimum time. Below that, it doesn't make any sense to say what is past, present, and future.
This is a good point to move on with the discussion. So we have some questions about today's talk, and this is a good point to switch, since what emerged already from this Q&A is the fact that the differences between their ideas of this fundamental of these approaches to quantum gravity is the difference with the principles. What are the principles that we keep? What are the guidelines that we use to build our theories? And this is a good point to start the open discussion. It is broadly about theoretical frameworks and guiding principles for fundamental physics, which is the topic of today's session, but in particular quantum gravity. And here we have 5 experts on quantum gravity, same theory, asymptotically safe gravity, causal dynamical triangulation, and different flavors of quadratic gravity, and also effective field theory in the case of John. And these are, different ways one can go beyond plain general relativity or gravity plus QFT. The plain merging of GR and QFT doesn't work at least in perturbative settings, so there is at least one shift that one has to make. And depending on the shift, depending on what exactly we change in our guiding principles, so we can get different theories, different answers. So to start the discussion, I asked all of them to prepare an initial opening statement on the status of theoretical frameworks and guiding principles in fundamental physics. So perhaps Benjamin can start with this.
Yeah, so also from the discussion and talks today, I think it's fair to say that we all like unitarity. It's probably one of the principles that is hard to get rid of. Maybe causality is one that you cannot get rid of. Maybe as an additional point there, if you study EFT, there's some interesting story there. You can get violations of causality as long as you cannot resolve them in EFT. So this gives you a bound on maximal violation of causality that you can have in an EFT. So I think that's maybe also one motivation why we are maybe a bit more open to violate causality than to violate unitarity. In terms of frameworks, I think I showed you my story. I think that QFT is not at its end yet, and it might hold some unexpected promises. And maybe we need to rethink all the arguments. Since this also came up in one or two talks, another example for this is quadratic gravity at a classical level. There are a few new results by Hill and collaborators who've studied quadratic gravity, classical quadratic gravity with numerical relativity. It turns out that, contrary to popular belief, you can write down an initial value problem, and in some part of theory space, you get a well-defined evolution. So this I find really interesting, and I think this gives us maybe a new perspective, and that we should keep an open mind.
Thanks, Benjamin. John?
The foundation of theoretical physics is experimental physics. We have to, as a phenomenologist, we have to recognize that when theory has been built on the lessons that we learned from experiment. And that's not to say that theorists have no role, but the theoretical imagination is larger than the experimental reality. There's an old story about Durkheim where he said that in the old days, theorists were very humble because they would propose some calculation today, and a month later they would find out that that experiment tells them that they're wrong, so they stayed humble early on. Lately, with the slowness of the experimental development, we have to be a little bit more religious in our viewpoints, and because we're working on some topic for a long time. The lesson of experiment that seems to be there at the moment is that are fundamental theories, the ones we understand, are four-dimensional, renormalizable gauge theories. They stand in bubble space, seems to stand in isolation. This leaves gravity as an interesting test case because it's the one that doesn't fit that paradigm at the moment. And you can see from the developments that have gone on that the theoretical imaginations have run wild in many directions, trying to understand it. It doesn't seem to be just a simple model building exercise like you might try to solve the phase transition or something. Seems deeper than that. So that's the opportunity for theory, and our experiment, we have some hope for experiments. I would think that gravity is potentially the leading candidate for deviations from our standard expectation. One of the slides I dropped in my talk was about the frontiers, both in gravity and in quantum mechanics. But maybe I'll stop at that point. I think there are opportunities both in theory and in the gravitational sector, partially because it's so hard to get it to fit into the conventional paradigm.
I think that the general danger is to make overstatements, which is something that, at least in my little own, I try to stay away from. And this has not always been the case, because if you make composed statements about something that you don't control very well, correctly other parts of the community react and criticize, which is helpful for my story. So my whole point, as I said before, was to challenge the current status of string theory on one corner where it doesn't seem to be so resilient, which is the breaking possibility. And in this respect, a priori you would have expected to find problems. And the problems are fewer than you expected, or they disappear. So in my view, this is a positive step, but I'm always very cautious with making big statements, especially on stuff that is not checked by the experiments all around. So this is my partly a statement what I said. It's important that we say it very clearly.
So as I said, in a situation where you cannot make experiments and collect new data, I think that the best attitude is the most conservative one with respect to what has been successful till yesterday. So the basic principles are, for me, the first quantum field theory, the general framework that worked, unitarity. It was, I consider it more or less a tautology, just demanding some closure. Then the other two are weaker. One is normalizability and the other one is locality. Normalizability is a recipe, so it's good for checking if you go somewhere. If there is a special theory with a finite number of parameters that closes the circle, that's the best candidate. You know, nature is not obliged to be simple for us. And then locality, which is a tricky thing because in the end a theory is never local, the quantum field theory. So that has to do with the fact that we start from a local Lagrangian, just because in the old days we used quantum mechanics, the correspondence principle. We knew that exploring the quantum world is tricky, and we hope there is at least a sort of correspondence with what we use classically. And these recipes, in particular locality, are what worked. And in my quantum gravity theory, you give up locality a little bit, but still in the most conservative way, because you have these purely virtual things that you may want to iterate out. And so below a certain scale, you give up what? Locality, analyticity, chronological order. But the rest survives. So I think that's pretty impressive that we as human beings can. There is another story, because you want to talk about general principles, but you may want to ask also about what is the purpose of. And in this respect, I have to add one thing: perturbative theory. That's another key for me. I don't claim I'm able to give any contribution beyond that. And what has been working for the standard model has been perturbative. So we have. Huh?
That's not true.
Okay, so then I will be happy. I will be happy to know.
The PCB looks nothing like the actual PCB.
Sorry. Okay. But I find, let's say, I'm interested only in perturbative physics. That's my choice. What I want to say is that we try and identify the problems we can solve, and the others are too difficult, and we ignore them. And the problems we can solve are a tiny epsilon of all the problems we cannot solve. For example, everything that is non-perturbative, what you will say, that I will also listen.
Thanks, Daniel. And then, Renata. Is it working?
Yes, I think it's working. Yeah. On principles. As long as I've been in the game, we've had these discussions about principles, and by and large, I don't think they have been terribly fruitful. Okay? So, people have argued, of course, without knowing what quantum gravity is, without knowing what to compute and how to compute, arguing about principles. I mean, there's no end to them. Of course, as soon as we go macroscopic, we are fairly sure what these principles are. They are the principles of standard relativistic QFT, and I don't think there's very much to argue one way or the other. But it's maybe more fruitful, and you get to this. I'm taking, of course, a strongly complementary point of view to Damiano, who is trying to stay perturbative, especially when you come from the non-perturbative. So, because then the question you have to ask yourself is, now imagine that people do believe in this quantum foam, some regime at the Planck scale where things certainly do not look semi-classical. But if you're now going to describe this in some way with the tools of theoretical physics, what is it now precisely, and what kind of statements do we expect to be able to make? So if I make a statement about, my theory is local or unitary, what does that then mean in operational terms? In quantum gravity, for instance, there's also another long-standing belief that is, I think, even held by a majority of my colleagues, that there must be some fundamental discreteness present at the Planck scale. And there have been, of course, not centuries of discussions, but decades of fruitless discussions. Yeah. So what you should ask is, well, how would I operationally, within the theory, could I do certain computations whose outcome is then maybe a discrete spectrum of a certain different invariant observable? So I think that's maybe one way of thinking about it, even before going to experiments, which of course we all have great trouble to do. So I wouldn't maybe focus so much on the principles, but on the other hand, I talked earlier in my talk about the non-presence of emergence. Once you start working with microscopic models, and emergence just becomes it's just wishful thinking. You wish so many things to emerge without having to put anything in, but it just doesn't work that way. Yeah, so we had the discussion about causal structure. So people have been standing on their heads, and even in toy models in 2 dimensions, you used to can something like time and or causal structure emerge? And there is just we haven't found any evidence of this happening, even in simple toy models, and you have to ask yourself, okay, maybe this is an overblown expectation. One of the very many overblown expectations that are around in the field, that because we are so unconstrained by an experiment, right? So our wishful thinking can just go anywhere. Okay, so I would focus on observables. Okay, observables as even as intermediate step to phenomenology. Observable meanings as a quantity I can compute, preferably in a theory that allows me to go beyond perturbation theory, something that's well defined. I can make certain statements, say about certain operators, observables of the theory, and then we can start comparing those. The problem is that with many approaches, one doesn't completely understand what the observables are, let alone compute them. But that is where one has to go. And we put some things on the table like the spectral dimension, and hopefully in the not too far future, some kind of two-point functions, where we have no idea a priori whether when you compute these things, if you're able to, in a very Planck regime, they have any resemblance with certain classical objects. But that's, well, at least it creates, something one could potentially observe and potentially look for classical limits of, and potentially compare between different formulations. So I would say key is, the winner must have strong computational capacities in their approach, or answers for quantum gravity must be able to go beyond perturbation theory, I think, because where else do we look for, radical new structures? And really what we see is, if we normalize your expectations when you're confronted with, this very strange kind of ground state of this path into in a non-perturbative regime, and you have to try and make sense of it, and you can show that to some extent it is possible, but it doesn't really confirm with your semi-classical or classical expectations of what observables are. Yeah.
Thanks, Renate. And Renate indeed raised a very good point. That is, we can talk about principles, we can talk about how our theories are regulated, but in the end we need to compute something and see how our theories do in the IR. Again, we reproduce what we observe in our universe. Can we compare the different approaches? But indeed, observables is a huge problem. One, because observables in quantum gravity is a question in the field. And the second, because of course we would need to agree on observables to compute. Because if Renate now computes quantum rich cursor and Damiano computes the tensor plus square ratio and someone else computes amplitudes, we have different observables and we cannot really compare that. So we would need to agree on something. And perhaps we could
And speaking of observables,
yes.
can I try to bring this discussion down to earth?
Yes.
At least close to reality. There are many different observables that you might think a quantum theory of gravity could shed light on. Dark matter, dark energy, structure formation parameters of the early universe, the nature of inflation, if it occurred at all. There are going to be many new observations of gravity waves in different domains. There are ultra-precise clocks that are going to give us new windows into how time works and how precise our understanding of time is. I'd like to hear from people who work on quantum gravity whether they think they'll have anything to say about these things.
Anyone wants to comment?
There is some link to what I was trying to say, because the behavior of the spectral index reflects itself into the structure formation story. We understand the structure formation in relation to the primordial fluctuations that eventually amplify and then make the structure form. What I was trying to show you is a possibility that there are, I called a post-diction the fact that the spectrum goes down, because I knew it went down, and I just didn't look for it on purpose, but we know the answer. And I showed you, perhaps in passing very quickly, that at that transition, something that we found in many instances can be justified semi-analytically. That was a WKB argument, if you want, for the sketching, that the tensor to scalar ratio should increase by an order of magnitude at the transition. And then I showed you that this computation that is not appeared, I mean, that's now I gave you if you want, the upcoming result, that the same parameter that determines the slope and therefore the weakening of the power of the first few multiples determines also the oscillations that the 3-point function you find in the equilateral or squeezed form. And in principle, you should be able to see an amplification of the result which is beyond the observable limit now for the non-Gaussianity. I didn't present it in that form on purpose, because the non-Gaussianity is presented as the 3-point function divided by the 2-point function squared. And for me, the 2-point function is reduced, so you get a free lunch because it increases. So I presented it as ratio of that result with respect to Maldacena plus 1, so which means correction to the slow case. So you will see oscillations and you will see an increase. And so I think that's something
that's a good example.
That's an example. You have a parameter, but the key point is that the parameter is already detected in another context. So the frequency of the oscillations in principle should respect that. If that model is correct. If it's not correct, okay.
Any other ideas? There is a question.
August,
Yes.
it's of course great, but you will never ever see it because of cosmic variance.
I know, I was very careful with that, saying that the transition that I see through this delta is around L equal 10.
Yes.
Those plots that I showed went down to L equal 5, because with the 3-point function it's worse than with the 2-point function. So 2, I brought it to 5.
And also the other thing, Maldacena calculated also completely irrelevant line because it's spoiled by subsequent evaluation of perturbations, which give you FNL, for instance, of the order of unity. It's not 1 minus NS.
But for the first multiples,
you have to separate two things. And it's impossible for that to have a huge sample. Of course, if somebody will put 21 centimeter detectors on the other side of the moon, okay, and people will go up to the redshift 1000, something could happen, but it perhaps will never happen, at least in our lifetime.
My understanding is that the high K portion of the spectrum is the one that is more affected by this subsequent dynamics. The first few multiples are sort of clean. You see there is a transfer function which is essentially a delta function.
Yeah.
You see the primordial spectrum. That's what I noticed to me. And I understand that cosmic variance is an enormous limitation.
But
I
yeah,
was careful to state that.
everything within this horizon after that actually is spoiled by nonlinearity of Einstein equations. And by factor 100. You see, because Einstein equations are nonlinear, but even this thing is non-reachable. Because we are on the bottom of Gaussianity, and you cannot extract anything because we don't have big enough sample. You see, it's outside of cosmic variance. Everything what was reached was reached. Unfortunately.
Can I say something about one quick question?
Yes.
So you listed a lot of some topics. So I can say something about the primordial universe because that's the natural thing where this change of theory, in my case, has important effects. You mentioned dark matter. I cannot say much about that because I don't know much, and I've studied that.
By the way, it's not meant to be as comprehensive list.
Yeah.
Off the top of my head. Other observations, people are now looking at what black holes look like.
Exactly. Black holes, I've not studied that because the first impact in this change of diagrammatics is on time-dependent objects. But the other, I have a question on the other things that you mentioned. You mentioned clocks and gravitational waves. Do you think that progress will reach the level where quantum effects become important? Because if yes, then I will have definitely to study that with my theories.
Why?
No, do you think you will reach in gravitational waves a point where quantum effects become important.
Definitely. Yeah, I talked about
That's it. And okay, then I will have to consider that.
But perhaps it depends on which type of quantum gravity effects, and you
Yes,
mentioned that it
there
depends.
are different levels of gravity effects. I mean,
Because indeed,
levels of just quantizing linearized gravity and relativity at low energies is the level at which
Okay.
you see things. We already had a chance.
Okay. Then probably my correction will not be so that.
but indeed, the quantum gravity corrections tend to be Planck mass suppressed, or whatever is the scale of the new physics suppressed. And then indeed, one question is what are the most promising channels to detect or see quantum see quantum gravity. And it would be nice to have, if you have any idea or anyone from the audience, what are the most promising channels? Ravan?
No, I think all the observations we are trying to target, either in the universe or black holes or quantum effects, or then the thing discussion in the Frank talk is about equation of state of neutron stars. Everything is associated with third space time, and in quantum gravity approaches, we kind of never deal with third space time. Always the questions about what happens in blank scale, but third space time effects are never taken into account. I'm curious if you think pure field of space time is the most essential thing before we worry about real quantum gravity, and that is the thing we should test it completely with observations. All the observables are related to third space time, not blank scale things. That's far away.
Yeah, so I would say many of these may just have nothing to do with quantum gravity. Understand it as a fundamental theory underlying, GR. So, and Frank, I talked before about wish lists. People have long wish lists. Well, we don't know whether dark matter and dark energy will ultimately explain by the theory of quantum gravity.
No, that's the question.
No, and I think I would say many of these things on these wish lists probably will never be explained by quantum gravity ever. That includes. Yeah, I think the closest is really not, okay, people put lots of hopes on, tabletop experiments to show the quantum nature of gravity. It's again something different from, Planck's effects, obviously. So, well, let's wait what happens there. But I think our best bet is still the universe. But there we have the fundamental problem, that Slava mentioned. Will anything survive? So if interesting things happened in the very early universe that are really from a quantum regime, will they be completely washed out? And I think, well, we don't know. When it comes to black holes, I think our best bet is that it's something just semi-classical, and quantum gravity will have very little to say about it. Never mind that it also cannot. I think in a non-perturbative sense it will have difficulty. And anything that's perturbative, as Alessia was saying, is just Planck mass suppressed. So we won't be able to test forever, basically, unless someone has to come to a very clever idea. So again, early universe and perturbations. Is it really true? In the best of my dreams, what can I say about, let's say, just the homogeneity assumption? How homogeneous are my quantum spacetimes? They're crazy. So I have to define the notion of homogeneity, and if of course it will deviate, but what is the measure of this deviation? And might that have ultimately some consequences right down the line when I study correlations? I would hope, yes, but again, maybe we won't ever be able to see them because they will be washed out by non-linear effects of what happens subsequently.
Maybe one point to add here is that the questions that you can reasonably answer might also strongly depend on your approach. So some approaches are more geared to answering one question, and other approaches are more geared to another question. So speaking of the asymptotic safety point of view, this is a quantum field theory approach. So naturally we are kind of more closely connected to LHC physics. And one point that I try to make in that talk is that at least in principle in asymmetric safety you can ask, do I get the right mass ratios of the standard model? Or do I not get it? If I don't get it, theory can be as nice as it is, in unitary, whatever, it's falsified. And answering that question might be much more complicated in a different approach. So,
yeah, that is a good point. Of course, we need to reproduce the physics that we know, and whatever theory of quantum gravity one has in mind, it has to be compatible with the standard model. Of course, ideally, you also might want to enhance the predictive power and reduce the number of free parameters in the standard model, but the very basic requirement is that our theories are compatible with it. So, do you want to add anything in this direction, or anyone else in the audience?
I just comment on Frank's list, which is the great list that we all keep in mind. I think we don't have any guarantees on any of those things there. And so hopefully we'll have some luck. But this is the list of things that are pushing us, and which is we're lucky.
Yes, for me, the primordial, the early universe is the challenge, because at that time, the size of the universe was precisely the size that's involved in these scales. That's not even Planck length. So that is where we have to concentrate to compare predictions and calculations. If somebody can suggest to me another area where I can make calculations, I'll be happy to do it, but I find it very hard.
Black holes? We don't know.
In black holes, as I stressed, the description, the approach I had doesn't change much with respect to the others. But it's definitely something I still have to look at. But do you really think we have a lot of data? I mean, because, you know, because, okay, but you know how long it takes to elaborate. It's something.
First there was Ilya first, so there are some. Okay, no, so.
Okay, I don't think that from primordial universe you have to expect anything of quantum gravity, because everything is settled down already there. But there is black holes really, if they would be evaporating, and if the area would be quantized in terms of the Planckian area, that even huge black hole would give you strong deviation from the thermal Hawking spectrum. It would be consistent of lines, you see. But the problem is to find these evaporating black holes with the masses smaller than 10-15 grams. If you will be able to find single one or three, then you get direct actually evidence of quantum gravity or for quantization in terms of the Planckian areas.
But why do you say that everything is settled about the primordial universe? Do you know the value? Do you know the value of R?
The value of what?
The tensor to scalaration.
I can tell you then, okay, there is good balance on the value of R. Yeah. And if you will even measure the value of R, it will not add you too much surely to your knowledge.
Then there are the tilts, then there are many
tilt, okay, you cannot determine in the range between multiple 80 and 100. And this is the only open window where you can, okay, remove foregrounds. Because there is B-mode of polarization at L larger than 120. There is B-mode polarization, but at low L also everything is saturated again by big cosmic variance. You see, at smaller. And there will be this bicep I'm not very sure that they will find something, but even they will find something, okay, it will not change dramatically the picture. Even if I would tell you that I measured, okay, air, tell me what you would conclude from.
Well, there are many predictions around, so many will be falsified.
No.
No?
They will be ruled out 1 million models,
Yeah.
but the other million model will come in.
Yes, that I agree.
But we don't want
but
models,
there
we
is-
want the fundamental.
Yes, because I understand that in cosmology, talking about fundamental principles, I understand that in cosmology you accept every model basically. You're very democratic, but I'm not that democratic. For me, I want something that comes from high energy physics. I want to merge high energy physics with cosmology. So for me, there is only one model that satisfies all the principles that come from high energy physics.
Sorry, but
And then-
cosmology is not a slave of high energy physics. You have to forget about it. Cosmology is a separate side.
Can I just interfere because there are several things that I don't understand I mean, putting aside that cosmology is finished and statements like that, which are
I didn't say that.
whatever you said, yeah, something similar.
Don't comment. Speak
Yeah.
what you
But
want
like
to say.
no, what I want to say is that actually measuring the tensor mode would be the direct evidence for quantum gravity. Because the scalar mode is not an evidence for quantum gravity. Scalar mode you can obtain as a fluctuation of a scalar in the background classical gravitational field. So therefore, I don't understand.
Wrong.
Yeah, okay, yeah. So one is the no, we can discuss it later. But this is extremely important to understand because one is the fluctuation and the other one is a Hamiltonian process, sort of, because it's a production of a graviton, literally, the tensor mode. So, does this work?
Yeah, it's working.
Yeah, and I think it's extremely important. Also, regarding black holes, you missed my talk yesterday. So, then there are other options. Black holes too. I know that you were sick, but no, this is a positive comment. That I mean, there are other options for black holes. I discussed yesterday this memory burden effect and things like that. And for sure, yes, black hole is one laboratory in which we can, okay, at least indirectly, we can see some imprints of quantum gravitational effects in the, for example, mergers and things like that. So yeah, that's, I don't think we should give up and say, okay, quantum gravity is finished. But putting this aside, the positive side, now we go to the negative side, because to make a prediction, you need to have a microscopic theory. And I don't know how to make a prediction in a theory that violates causality, or like sacrifices the basic fundamental principles of quantum field theory. I mean, I don't want to, so it's very important to, it's like, I don't want to confuse open-mindedness with necessarily trying to propagate some absurd, because when you tell me that you violate causality, I don't even know how to work with these theories. I don't even understand what it means to make a prediction in a theory that violates causality, because physics has to be reproducible. If you are making a prediction, I should be able to go home, do the same calculations, and get the same results, and not to depend on like some kind of like assumptions which continuously change and things like that. And that's my main problem with these exotic approaches to quantum gravity, which sort of say that okay, we should. I mean, I'm open-minded. I admire new ideas, but I just don't see how to work with those things. So.
Were you here a little time ago when I explained Dirac's idea about the violation of microcausality? Were you here? Did you listen to that?
Yeah, you told me even personally.
Okay, so that is an example of how you can work when an equation violates microcausality.
I'm not satisfied with
I
that.
will tell you a little bit more. Basically, you have a violation of microcausality within a certain range. You need to anticipate, let's say, the future, 10 to the minus 36 seconds, to predict the future in 1 second, let's say. So you just make a bet that nothing will happen in 10 to the minus 36 seconds. Period.
So was that a follow-up or a new point? Because we have a new point by Ilya first. So okay, then Ilya first.
Yes, I have a kind of.
You have a follow-up? Yeah. Maybe very briefly follow-up by Howard.
Very short comment. So, causality in a very general sense basically means that given your evolution equations and given initial data, you have a unique prediction for any future event or whatever, basically, any future time. So is that satisfied by the construction that you have, or is that violated? Or
No, you violate my causality, so you make this kind of bet, which is similar to the bet you make when you talk about any prediction in special relativity. Because as I stress again, the only thing you can know about is your past lifetime. And in a second, that will be larger. So something can sneak in all the time. So strictly speaking, you cannot make predictions in special relativity. Let's face it, this is the reality. Still, we can make complications.
Okay, maybe let's switch to a new point now.
Yes, my question is a bit maybe provocative and also more fundamental. We are always assuming that the laws of physics are unique, but principal relativity tells us that reality depends from the point of view from the reference frame. So, what I mean, we have quantum mechanics, which has a behavior which is statistically, so there is no deterministic behavior, and we have generativity, which is very deterministic. We don't understand how to combine this together. But are we sure that if we would be smallest particle, the behavior of, for the behavior of particles from the point of view of particles would follow law of quantum mechanics, or quantum mechanics is what we see because we have in a completely different scale. So our perspective, do you understand what I mean? I mean that the quantum mechanics behave as we see because we are looking at phenomena on a completely different scale from us. Instead, on macroscopic scale, which is our scale, we have the classical behavior. So what I'm saying, are we sure that quantum non-deterministic behavior is not an effect of a completely different scale of our perspective? It's a provocative...
No, I understand that is a deep question, but to some extent I am more practical than that. I do not focus too much on words, because the same way as you say that physics doesn't depend on reference frame, you know very well that physics doesn't depend on our own words. Interpretations of quantum mechanics, what you fill in virtuality, if you want you can use Bohm, all local variables, we don't care. In the end, you just compare data, and that is what cuts out this kind of discussion. In my view, but I wouldn't be able to answer that kind of question.
I just comment that, like all theories, there are limits to our knowledge about quantum mechanics, and the suggestion that you're making could be described as how well we know the various limits. As was said in yesterday's panel discussion, there's really no reason that we know of at the moment to change any of the rules of quantum mechanics. Everything seems to work perfectly well. Well, that doesn't mean that isn't the right thing to do. It could be that the formulas that we know, the rules of the present we work with are not the complete theory, and that there is some other theory that could be some other extensions that could be used for this story. Whether that's true or not is a determined.
Well, another point is that perhaps whether we will see quantum gravity in the near future is what is the scale of new physics. And perhaps Augusto here can comment a bit on that, since in theory there are two scales. Fundamentally, the G scale is not really the blunt scale, but the string scale. And that means, to my understanding, it will be below the blunt scale. So do you think that we could see quantum gravity?
Because of that difference, the scale of string scale and the Planck scale are separated by this coupling constant, which is the expectation value of the electron, which is the dynamical quantity. It's one of those cases in which you cannot say anything else in general. For instance, if you have a non-trivial vacuum, the electron changes point by point, like in the case I told you. There are some regions where it's strongly coupled, some regions where it's weakly coupled. So in that case, it means that this string scale in Planck scale
microphone closer to your.
So yeah, I mean, if you keep the Planck scale fixed, then in this case, the string scale moves you to the context. So I don't think you have to make, at least I'm unable to make an absolute statement. It's true that there are different scales. It's true that one is smaller than the other, but it's also true that we base this observation on the fact that we like a small coupling to which observation here. And as I told you, we will not really back that this separation is not necessarily so sharp.
Not even if you specialize to specific settings like cosmology?
No, because in cosmology also the dilator evolves in these cases. So it's true that the dilator in these cosmologies has an upper bound. So the scales indeed are separated, but the separation is dynamic. What people have in mind is static applications like Campagna or spaces, chloride or orbifolds, where you go down in 10 or 4 dimensions, and it has an effective in 4 dimensions, but in those examples, it's a modulus. So if it's a modulus, the way it is that is the interest in this case we have to consider, because what is a modulus is predicted to the second scale. The dilator is not sample, it's a response. So it's
Okay. Anyone wants to add something on the question of the scale of quantum gravity?
If I can make a comment as well?
Yes.
So, I want to just make a comment that in general, the scale of quantum gravity and the scale of physics do not need to be the same. For instance, the example that the most is the one that John and Damiano are kind of following, although they are pointing in different directions. And I would also plan another third direction, but I don't want to end it there, which is the one that starts from the principle of strict minimizability. In that case, you have general relativity that you treat as a probability, as a conflict here at an effective level, and then you say, okay, I want to go beyond that. And of course, people immediately say, okay, then we need quantum gravity to go beyond that. But if you just ask for renormalizability, what renormalizability tells us that you need to add something to your starting Lagrangian. In this case, would be the R squared term and the Y squared term, which of course they introduce new scales, which are the masses of this additional piece of freedom. But these two scales in general are not scale of quantum gravity. They can just be scale of new physics. And the physical example that we have is the one of the Starobinsky scalar mass, which is 13 GeV. Now, in this case, if we take renormalizability as a guiding principle, you would say, okay, beyond general relativity, the scale of new physics, if there is nothing else, would be the mass of this scalar, which is very important to explain, for instance, in the unsolved in this case. But the scale of quantum gravity, where you see really like purely quantum gravity effect, would be a different one, would still be maybe one scale. And this does not mean that you will not see quantum gravity in the large limit, you can still see it, for instance, through gravitational wave or through this laboratory experiment we are trying to propose. So in general, the two scales, just to connect the question, the scale of new physics or the scale of quantum gravity could be a completely different one. And that's an example of in the quadratic gravity approach that was mentioned.
Yeah, thanks, Luca. Other questions or points? We see one there.
Yeah, just a curiosity, if someone of you might comment about low energy tests of gravity
and the possibility of having indication on the fundamental nature of gravity, whether it's actually intrinsically quantum or not. When do we expect to have some result? And what if we have no indication about the quantum nature of gravity?
Anyone wants to comment? I mean, I guess everyone. Yes, someone already mentioned that. I mean, I guess that in this round table, everyone believes that gravity is quantum. But there are tabletop experiments that try to answer the question of whether gravity is quantum or not. The question is, what do we learn from that beyond the simple yes or no?
So maybe we can make another comment. So again, we discussed with Alessia this last year. So we should also distinguish the question of like testing quantum nature of gravity and testing quantum gravity approaches, because you can test quantum gravity, but still you will not rule out an approach, because you can just have like large quantum gravity based on gravitational waves, where GR is still a good description, or this laboratory test where still GR is a good large description. And so
you can test if there is entanglement.
right, yeah.
So,
but that is simply a test of quantum GR, quantum energy. And maybe to like test, let's say, quantum gravity approach in this case, because what we have seen today, it may be that even like a classical, for instance, I don't know, we don't need like maybe quantum gravity prediction to rule out some or test some quantum gravity approach. That's what I want to say. Like, so we can have like
which tabletop experiment? You mean the measurements of Newtonian law?
yeah, basically I think that
yeah, you can, for instance, with condensate, you can measure it.
So tomorrow we will have actually a talk on this, on
so
different
maybe
proposals.
there will be more discussions in that direction tomorrow, because tomorrow is about quantum and gravity. So
you mean the
one induced
entanglement induced by gravitational interaction between two masses.
That's one.
This is,
yeah,
also Frank mentioned one.
Yeah,
but this will be.
And the other one would be one of like the analog of the photoelectric effect, but with gravitons, that also Frank was mentioning yesterday, where basically I have like a gravitational wave heating up Werner bar with reduced gravitons. But maybe we can go back to that tomorrow, because it will be a session on that.
So now we are.
really said, just listening to the experts, because I'm not an expert on this, I think it's very subtle, actually, the theoretical arguments, and people are arguing whether certain experiments that are proposed as genuine quantum tests, are they really, or are the channels, ultimately classical? So I think
they're not.
There are people who, but it's disputed, right? Also recently there was some paper said, oh, all the old arguments by Dyson is all wrong, we just propose some,
I think they test classical deviations from.
It
would be a breakthrough on its own.
It's subtle and it's disputed. Maybe we can agree on that.
I would not dispute it.
Okay, at this point, so I mean, it's almost 5, so we should, unless you want to ask something, but
tomorrow there will be the
yeah,
second part.
Tomorrow there will be a big discussion on this, so maybe we should, maybe we should go towards converging on the discussion. So I mean, here we can clearly see that at the fundamental level there are disagreements on what the basic principles should be. There are, of course, possibilities for future observational channels, but these may also be dependent on the specific approach one looks at. Some things may be easier to compute in one theory or another, but there is also the general question of whether one should just first construct a theory that is fully consistent and then think of observations, or whether the two things should go hand in hand at the same time. Here, again, there are disagreements. But so out of all of these disagreements, I would like now the speakers from today to have one final statements for what their wishes are for the future of their own field, like own approach to quantum gravity, and what are the important milestones that could be that are reachable within in the next 5 to 10 years. Anyone wants to start? What to say? Maybe they're not reachable.
I think that's a homework for Portugal.
Oh, it was in my email. Or if it is not reachable, what are the important milestones that one should really reach in the next years if you would have infinite computational power? But anyway.
Yeah, I think so. In asymptotic safety, I'm not sure how realistic it is in 5 years, but really getting our hands on a first scattering amplitude computed from first principles and checking at the level of the amplitude whether it fulfills asymptotic safety. So whether we see, the great fall off, whether we see unitarity and so on, whether we see causality, and that of course requires Lorentzian signature, as I mentioned. I think that would be great. And even not even talking about full standard model or whatever, give me a scalar field, coupled to gravity, and tell me how it scatters gravitationally.
And I know what I'm curious about it, or doing myself, but that's not really the issue. I guess if I'm trying to answer your question, I'm hoping for a surprise in any of the approaches that gives us new insights greater than we've had now, and especially if it is experimental.
I would say that so far as string theory is concerned, the real issue is to make the so-called revolutions a bit closer to completion. There are many holes. For instance, how come we are satisfied with the fact that some theories link to one another, as I was stressing, in 10 dimensions, which is a great achievement, and then they are linked to something which is not in this case? Are we missing the fundamental degree of freedom? In some sense, we have two evidences, that one and the one I gave you about the linearly realized supersymmetry. I know no examples where linear realizations don't come as linear to the linear one. Please correct me if you know some counterexamples. For me, there are always limits of linear mass. It means that you take the standard model, the Higgs becomes very massive, and you get a sigma model. You just forget about it. But in some sense, if you look closely, the model is there, it's very massive. So in some sense, there are some degrees of freedom that are missing. This is, for me, is the deepest challenge. The rest is
So my wish is from the experimental, observational point of view, because there is a lack of data, not so much a lack of theory. When I speak with the experts in primordial cosmology and observations, they tell me that it is very, very difficult. It's a very challenging problem. So I think there is breakthrough at the practical level are welcome, and that is what I'm hoping for. Otherwise, it will take a lot of time, many years. But if that's all, we have to be patient and wait for what comes from data, because that is the missing part.
Yes, I would strongly advocate counting on actual computation beyond perturbation theory, so the kind of that is serious advocating. For instance, to compute, can we actually compute like curvature correlators in 4 dimensions in this fully non-determined field, and what will they tell us? And I hope, exactly following what John said, there ought to be some surprise. If there's if everything, we have already guessed 1,000-fold what can be extrapolated on the basis of our perturbation arguments. So if there's anything new, it ought to come from there. And as an example, I would give this thing about the spectral dimension, right? So, yeah, imagine space-time at the microscopic level is just 2 dimensions, but that's really a completely non-perturbative result because you don't get there by 4 plus epsilon. Yeah. So, and then you can think, okay, what potential phenomenological consequences might that have? So, find a surprise somewhere and then go and maybe look take that as inspiration for what observables, maybe even in standard astrophysics, maybe even some things that my colleague Mukhanov hasn't considered.
Okay, so this was a very interesting discussion in my view. So let's thank again the speakers of today. And the